Hello everyone, Aaron here, and welcome back to Leetcode. Today we are doing the kth smallest element in a sorted matrix problem. So, let's jump into the instructions. Given an n by n matrix, where each of the rows and columns is sorted in ascending order, return the kth smallest element in the matrix. Note that it is the kth smallest element in the sorted order, not the kth distinct element. We must find a solution with a memory complexity better than n squared. So, n squared would be copying the whole matrix. So here, 1, 5, 9, 10, 11, 13, 12, 13, 15. Elements of the matrix, if we were to write them out in order, look like this. So 1, 2, 3, 4, 5, 6, 7, 8 is this one. We know something about this matrix. So for example, if we were to look in index 8, 1, 2, 3, 4, 5, 6, 7, 8, that happens to be the same here. But notice this 12 and 13 are in a different order. So one thing we could do is flatten this matrix into a list, sort the list, and then get the 8th positional element. That is going to use n squared memory, and it's going to use n log n time, because that's the fastest way you can sort these things. I guess you could argue you can do it with n time with this. Sorry, no, that's going to be n squared log n. Because it's going to be n squared elements that you're sorting, and that's the fastest way you can do that. However, we know that every row and column is already sorted. In particular, 1, 5, 9 are sorted, 10, 11, 13 are sorted, and 12, 13, 15 are sorted. So we can take another view on this, I think, and that's that we're actually doing a merge sort. Now a merge is not going to be n squared log n, it's just going to be n squared. Because I'm going to look at the 1, the 10, and the 12, but I don't care about the rest of these things. And then I'm going to look at the 5, the 10, and the 12, and the 9, the 10, and the 12. Because I know each row is implicitly in order, I don't need to keep searching the whole row, I just need to search the front thing of each order. The current element of each row that I'm looking at. And then we're going to keep that up to count that up to k, not all the way at the end, because once we've found the kth element, we're done. Then the question becomes, can we do better? Well, so one thing we can do to avoid using n squared memory is we don't actually need to do the merge sort. We just keep track of what we would do to do a merge sort, and then just don't actually do the merge. So that when we're going to fill in what would be the kth element in the sorted array, we just return that element. We don't actually say we're at the second element, and that's before k. We don't actually put that one into the right position. We just carry on over as if we had put it in the right position. I'm wondering if there's a bounding we can do as well. So because we know these are in order, we don't need to start at the beginning. So hang on, if I just to exemplify what I'm trying to say here, if I draw this out, let's do this, 1, 5, 9, 10, 11, 13, 12, 13, 15. The earliest the 8th element could come would be 1, 2, 3, 4, 5, 6, 7, 8. It would have to be on this diagonal, basically. Or, well, no. It would be this diagonal or later. If we had a whole lot of repeats... No, actually, we do know it's on that diagonal, don't we? Somewhere on this diagonal is the element we're after. So, for example, if I was after the 5th smallest element, I know it's going to be somewhere along this diagonal. Because 1, 2, 3, 4, 5 is 11, it's that one there. If instead we had 1, 10, 20, 2, 11, 21, 3, 12, 22, 1, 2, 3, 4, 5, no, the 5th smallest element there is still that one. Let's go with the 4th smallest element. So in this original one, 0, 1, 2, 1, 2, 3, 4, it would be this one here. Whereas over here it would be this one. So it's 10 in both cases by pure coincidence, but they're always on this diagonal. So what that actually means is for k, we can compute all the indices of diagonal that it would actually be on. And then we just need to find the minimum on that. Do we need to find the minimum of that diagonal? If it was a 10 and a 5. Hang on. No, it's the maximum on that diagonal, isn't it? No, that's not true either. How do I know when I'm looking at a diagonal which one? So here, obviously, it doesn't matter. I'm looking for the 8th smallest one here. 1, 2, 3, 4, 5, 6, 7, 8. It's 21, not 12. Because if I was looking for the 6th smallest element, we know it's on this diagonal. So I just need to work out what the... No, hang on. Yeah. $12 or 21. If I'm looking for the 6th, so these are 6 and 8. If I'm looking for 6, I want the smaller one. If I'm looking for 8, I want the larger one. On these ones here, if I'm looking for the 4th smallest element, these are 2 and 4. Ooh, hang on. No, because there's another example here, isn't there? 1, 2, 4, 3, 5, no, 3, 6, 12, 5, 10, 20. 1, 2, 3, 4. I don't know it's on this diagonal because there it's up there. All I know is it's this diagonal is the earliest frontier. Okay, so we wasted a bit of time doing something wrong there. Anyway, let's get the core going. Let's do... Okay. No, we'll count down from k. Index is equal to 0 times len matrix. And what I want to do is effectively while k is greater than 1, in fact, while k is greater than 1, I want to do something, and I want to return matrix. Oh god, I need to do return a deep index into the matrix. No, hang on. Hang on, I'm getting myself a little confused here. So what I want to do is all the indices, 0, 0, 0, 0, 0, 0, 1 for each of them. And then what I want to do is I want to move these forward, and in the end I'm going to be left with k is equal to 1. I'm looking at the right one, and then what I want to do is I want to return the minimum of matrix I j for I j in enumerate indexes. So 0 gets indexed at 0, 1 gets indexed at 0, 2 gets indexed at 0. The minimum of those is what I want now. So while I'm in here, I'm filling in that kth position in my sort for merge sort, yada yada. Then what I want to do is I is the min. Let's do this again, except it's going to be j I for I j in enumerate indexes, but this time I want to make sure I'm just getting the index. Indexes I gets incremented by 1. So the logic here is I'm looking at the 1, the 10, the 12. The minimum of those is the 1, which is at position 0. So I want to increment that one forward. So now looking at the 5, the 10, and the 12. And so on and so forth. The 5 is again the smallest, so that gets incremented. I'm a little bit nervous about this actually. Because first off, I need to make sure I'm looking at matrix I j. If hang on, n is len matrix. J is less than n, else infinity. The reason I'm doing this is basically if I'm going to step off the end here, ignore it. Basically, it will never be the smallest thing. I'm going to set it to infinity. I've stepped off the end. So stepping through this, n gets set to 3 in this case. I'm going to have 3 zeros, 1 for each row. While k is greater than 1, k gets decremented, so it starts at 8. This is now set to 7. Then what I want to do is I is the minimum. So I is the index of the rows where it's the smallest of the keyed value in each row. 1, 10, 12. It's going to give me 0 because row 0, the first row, is the one that contains the smallest value. So then it's moved along. So now my indices is 1, 0, 0. Then it's going to compare the 5, the 10, the 12, and it's going to see 5 is smallest. It's going to go to 9, 9, 10, and 12. That's still going to be smaller, so that gets pushed off the end, effectively. If j less than n else float. Oof. You know what? Let's just call it that. This is going to be val ij. This one is going to be val ij. I think that's how you do that in Python. Let's quickly run this. I'm not super confident at the moment. Ooh, seems to work. Let's use all the test cases. Nice. Let's use this one again. But no, let's use one of our other more unusual ones. 1, 2, 4. 3, 6, 12. 5, 10, 20. Asking for position 4. Seems to work. What happens if we ask for position 7? So what's the complexity of this? Because down here, there's some follow-up. Could you solve the problem in constant memory? It's not quite constant memory because it needs these n indices floating around, which is a bit of a pain. Could we solve it in order n time? No, it's still order n squared. So at least it's not order n squared memory. That's an improvement. Anyway, let's submit this because it seems to be working. Fantastic, it worked. Could we do better? Let me just think for a moment, because this solution isn't terrible. If I was to look at this, I could look at it and kind of understand what it's doing. I think there's something to be said about once I know roughly where it can be, I can ravel in a specific way, I think. Like once I know where the frontier is, I've got quite a lot of information. Is that it? Do I know it's somewhere on this frontier? I know it's a 5, a 3, a 2, or a 4, for example. So it's not just the diagonal, it's the whole frontier within the matrix. I think I do know that, actually. So here it really is truly, sorry, this one here, it really is truly this diagonal. But out here it's not this diagonal, it's this whole frontier. Or could it be here too? No, I think it has to be like this. Could it ever appear there? No. So I think there's something here. And then I don't need to... Once I know it's on this frontier, each of these could be the kth element. And once I know that one of these is the kth element, I work out what their min and max indices are. No, hang on. If I know... Yeah. If I know what their min and max indices are, as in, like, put in sorted order, these vary between, like, 3 and, well, if I'm going for K4, I don't really care what it goes up to. But I know the minimum here could be 3. So then I'm just looking for... I'm looking for position 4, and I know the smallest is 3. 1, 2, 3. I'm looking to put these in order and then go up 1. No, that's not right. Because the smallest is 2, isn't it? 1, 2. So yeah, no, the 1. Yeah. There's something there. I'm rambling. We're done. Problem solved. This is a valid solution for problem 378. I'm going to leave it there today. I will see you next time. Bye.